Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
So I'm very pleased to introduce Yongxiang Liu. We've been working together as technical co-chairs of ICME Multimedia Conference next year in Seattle. But most of the time he spends time as an associate professor in the School of Electrical and Computer Engineering at Purdue. And today he will share with us his passion for cameras everywhere.
Okay, thank you very much. Thank you for giving me the chance to come here and talk. Actually, I was here before. I was the room next door. Last year, when I was a speaker in the eScience in Cloud workshop last year, and that was me in the middle. I remember another room similar to this, and I was captured. The video was very nice. At that time, I told some people, I will be back, and here I am. Today, I want to share with you some of the progress we have made in the last 1.5 years. I also want to discuss some ideas. It's always good to hear people from different views. And we're actually building a system a lot of people to use. So you are welcome to be users and also collaborators. Actually, Jerry and I already discussed some ideas. Please feel free to interrupt if you want to say anything. So I started the project almost 4 years ago when I think about we travel. How many of you are gold members of any airline or has been a gold member? Looks like Microsoft doesn't send you to the Okay. You're that's much better. Okay.
I'm not gold.
Okay. So as we go to conferences, sometimes I feel that, okay, it's great to go to different places and learn their culture, the people, and so on. But sometimes we encounter problems like this: lost baggage, delayed flight, canceled flight, overcrowded trains, and so on, right? So I asked a question: can I see the world at my desk without going anywhere? Of course, I don't get the experience of the food and the people. But if I just want to take a look of the famous architecture, maybe that's good enough. So that was one of the motivation of the project. Now, I know some of you will ask the question, does a street view solve the problem? Let me give you a story of myself. I took sabbatical in Singapore, and then after that, I went to Singapore again twice for a conference. And as some of you may have been to Singapore, know Singapore is a very expensive place. And you can easily spend a few $100s for a decent hotel. So I was looking for a hotel, and I find a hotel that looks reasonably nice. It's a 4-star hotel, and that's a street view. So I thought, what a good deal. So I booked that hotel. But when I arrived, the taxi driver couldn't even find the hotel because the road was closed for MRT construction. If you come from the United States to Singapore, you know you always land between 11:50 p.m. to 1 a.m., right? Because of the time difference. So it was very late, and I find hard to find a hotel. Finally, we found it. And the next day, I tried to catch a little bit sleep. The construction started at 7 a.m. So I was thinking, okay, that doesn't seem a very good decision, right? I look at the previous example, and I made a decision based on this information. But the reality is the information was obsolete. So this is a picture I took just a few days ago. You probably recognize this intersection, right? It should be just outside here. And it actually tells you it was captured more than a year ago. This is another example. It's outside my office at Purdue University. This is the Northwestern University. I mean Northwestern Avenue. And there is a building there for 3 years. The construction started 2013. The building has been running. It tells us that the image was captured 6 years ago. So the problem here is absolute data may make us make wrong decisions. So suppose I tell my friend, I said, okay, so if you see the parking garage and then my building is next to a parking garage, then my friend will say, well, I look at the street view, the garage doesn't exist. I mean, the building doesn't exist. I see the garage, but building doesn't exist because it's obsolete data. So as a researcher, I ask the following question. Is there a problem? The problem is obsolete data make us make wrong decisions. So I want to have real-time data. And I see there are opportunities for research. So the question is, millions of images and video clips, and many of them are continuous video, are online. What can we do with the data? And what difference does real-time data versus obsolete data make? I already gave you a few examples of obsolete data that can cause problems. Yes, please.
To that point, how often are the street view images updated, if at all?
So the question is, how often is the stream data updated? Depends on sources. Some places, such as California, the highway data is streaming video. I didn't calculate the frame rate, but it's many frames per second. I will show you a few examples of the data in New York City. That's about 1 frame per second. And for Colorado, I'm talking about traffic camera right now. For Colorado, it's about once every 2 minutes. So it varies.
No, but the street view thing that you...
Street view?
Yeah.
Okay. So you're talking about street view. Sorry, I misunderstood the question. Actually, different companies have different update rates. Some company, this is from Google. They actually have a map showing you how old the data is. West Lafayette is not a very big city, so I guess it's updated very rarely. Actually, this was updated at least once because when I started the project, the data was even before 2009. But then, for some reason, they updated 2009. Some bigger cities are updated more often, but I don't have a very precise definition how often they update. Does that answer your question?
Yeah.
Okay. So so we started the idea of using network camera. The idea is the following. There are many network cameras. A study by a company called market.com. They estimated about 20 million network camera installed per year at about 20% rate increase each year. This network camera can stream data 24 hours. And we handle, in my project, we deal with only public data, meaning there's no password for obviously legal reasons. We don't want to deal with anything about private data. And this may reveal a lot of information about the world. You can also think about mobile data such as from phone or dash cam, and if they are connected to a network, we can also call them as network camera. Today, you can buy a dash camera with Wi-Fi capability for about $200. Now, let me show you a few examples of what network camera can show you. Yes?
Analyze in real time. Who's doing the analysis? And what sort of analysis?
Our group is doing analysis, but we also make our system available to other people to do analysis. So what kind of analysis? For example, you can count people, you can count cars, you can detect things.
So when you say you, it means the customer of your infrastructure.
Our system, yes.
So they have to write their own code or something to do these things?
Yes, we give you some samples, and then you will modify the sample programs to do what you want to do. Let me show you a few examples of some of the network data. This is captured. As you can see, it was about 1.5 months ago, October 7th. If you search Panda Cam, then you will find one of the examples here. This is the National Zoo in Washington, D.C., and they have 4 Panda cameras. I don't know who is doing the tracking. I don't know if it's by computer or a person. But then you enter another room, you can actually see the panda. So if you imagine that you can do a study of animal behavior without going to a zoo, that opens up a new paradigm of doing research.
You said you don't know who is doing the tracking.
I do not know who's doing the tracking.
But something is happening there that when he moves to a different room, the camera
Yeah.
just switches to that.
Somebody is moving.
The camera is
No, but
moving.
then when he goes to a different room.
Oh, as it goes to a different room, it also changes.
They might be doing
I don't know
something.
it's tracked by computers or somebody's control it. But you can see it. If you have a computer right now, do a search, Panda can national zoom, you'll be able to see it. So this is an example. Let me show you another example. This example has a lower refresh rate, so you see people are kind of jumping. But you can use this example to study. This is actually from Romania. You can see from the URL. You can use this to study human behavior. Actually, I'm working with several professors in psychology. They want to observe human behavior non-intrusively and also across different cultural environment. You can imagine you can sit here in the United States and observe people behavior in Romania. For example, do they come as groups? When do they come? How many of them at a particular time do they bring their children? And can you tell their age group? That has significant impact on how you design your marketing strategy. Because maybe in the morning, the age group will be different from in the evening. We actually have talked to a few people in near Purdue, some store owners. They say they do see the change of demographics, and they want to use that information to improve their marketing strategy. This is another example. As I mentioned earlier, I want to see the word. This is Yellowstone. If you have been to Yellowstone, how many of you know where this is? You know the name of that?
The prismatic spring.
This is?
That's the main
The
geyser.
prismatic spring.
That's Old Faithful.
Oh, it's the old.
That's Old Faithful, yes. This was captured in October. Now it may be covered by snow. But actually, I actually went there, watched them remotely in February, and I see it's covered by snow. I still see people sitting there waiting for Old Faithful. I was pretty impressed. But as you can see, these are all kinds of examples where you can potentially use the data without going there. Let me talk about the psychology study again. So several professors want to use the data to do a worldwide study. The hypothesis is people in different cultures behave differently. And you can do this study without sending graduate students to 10 different countries. Right? Of course, they want to go, but we don't have the funding. These are Washington State. These were captured a few days ago, as you can see, November 28. If you want to see whether a particular highway is congested, or you see where there's a long line there, just this morning, a professor sent me an email. I haven't read the detail yet. Being a few days ago announced they have 30,000 traffic camera on the map now. And I already mentioned some of it. So as you can see, this is an example of the same shopping mall at different time. You can look at the time. It's a bit small, but you can look at the time and study maybe how the customers may change. This is a volcano eruption in Hawaii. It was captured by the National Park camera. Let me show you it here. It's at a 15-minute interval. This was captured on January 24th, 2014. So you see the volcano eruption. Of course, that's a very active volcano, so it happens very often. But nobody was there to do the recording. But you can still watch that. So I think I gave you enough examples about those events. And also, last year we did a study. This used the camera in New York City. The left side of the figure shows the parade route. It's a Thanksgiving parade. And right side shows the location of the traffic camera. And we captured the parade on that day by selecting specific cameras. I would claim, using network camera, first you can see the parade without going there. Second, it's even better than you go there. Because first, if you've been to any parade like this, either you need to go very early, or the only thing you see is somebody's head if that person is taller. Even if you are tall enough and you stand there, you can only see one place, right? You cannot physically be in multiple places at the same time. But here we have 4 different angles of seeing a parade. There are actually quite a few cameras along a route, so you can see them. I hope that gave you enough ideas about the possibility of using network cameras to do all kinds of things. This is air quality in Washington, D.C. I was in ACM Multimedia in Australia a few weeks ago, and I noticed their taxis also have camera on the side. I'm not sure what's the purpose, but I noticed that. And this is another study by a research fellow in Australia National University. They have a camera looking in the forest, see how the trees change, and it's using solar power. And he's happy to share the data. So now you can imagine you can do a study of a forest without going to Australia. I'm going to skip that. We are not the first project doing this. Actually, some people in St. Louis have been doing this for quite a few years, but there are quite a few differences. First, they give you data. Second, the data is very low frame rate. Over almost 10 years since 2006 to now, they get 800 million images. And in a few slides, I will tell you, we can get 800 million images in a day because of frame rate. So that's what they can give you. So now let me introduce the project we are working on. It's called CAM2, Continuous Analysis Many Cameras. Yes?
So just the examples that you gave, how did you get the list of the cameras that are publicly available?
We search online.
Okay.
So the question is, how do we find the camera? We do a web search. We went through that several different types of strategies. The first, our project started by scanning the IP address at Purdue network with the permission of Purdue's network security. They say, okay, we know how to do it, go ahead and do it. So we find like a few dozen cameras that way. How do we find? Basically, different brands of camera have a specific signature. So we send a query. If the camera responds in particular format, we send out the camera. So we started by doing that. Then we also scan a few universities' IP address. We find a few hundred cameras that way. One university complained. They noticed that we are scanning their IP address. But that was too slow and basically too slow because the chance of success is very low. Then we started working on traffic cameras. Why do we use traffic cameras? Because you go to a state, you figure out how the data format, you get a few hundred or a few thousand at once. So that's another strategy. Then the third strategy is we actually have an agreement with a few companies. They have their data online, and then we get a permission to get data.
So what fraction of these are sort of 30 frames per second camera versus, once?
Okay, so the question is, what's the ratio of a high frame rate versus low frame rate? We actually don't have a precise number. I would say maybe 5 to 10% give us 30 frames per second. And I will show you in a later slide. That depends on where you are talking about. If you have a camera in United States, you try to get data from using a machine in the United States, you may get 30 frames per second. If you have a camera, exactly the same camera in Europe, you try to get the data in US, use a machine in US, you don't get 30 frames per second. I will show that in a few slides later. Does that answer your question? Yeah. Okay. So majority of cameras we have are updated once every several seconds to once every several minutes. And we don't have control over that. So this is our project. You are welcome to register as a user. When I received a grant from National Science Foundation in July, the program manager really pushed me hard. I won't give you a number, but he gave me a number, how many users we want to target before the grant ends. So I hope everybody signs up so we can get that number up. Okay, so go to our website and sign up as a user. Our system is not an archive of data. In fact, we don't retrieve data regularly. We retrieve data only when you ask us to retrieve data. Our system is a computing platform for doing image analysis in a large scale. When I say large, I show you an example here. We used 17 Amazon instances. We also use Microsoft Azure, but in this particular case, we use Amazon. Over 24 hours, we grab one image every 5 seconds from 16,000 cameras worldwide, and we get about 7 terabytes of data. We are working on getting 1 billion images over 24 hours. We encounter some limitation about our program because we need to spend more than 1 zone in Amazon. But we think we'll get there very soon. We are able to grab 200 million images and do some relatively simple analysis. We call background subtraction. The key here is not the image analysis itself. The key here is being able to do image analysis at this scale. Yes?
You mentioned something about zones. So the 17 Amazon instances all in
one zone.
Site, one zone?
Yes.
Why do the zones matter?
Because the account we got from Amazon restrict to 20 instances per zone. So basically, we just need to modify our program so we can get from multiple zones. We got a research account from Amazon. We also got a research account from Azure. Some of the data later you see will come from Azure. So this is the background subtraction program. As you can see, it's relatively simple, but you can replace that simple program by many other things. So the purpose is not the image processing itself. The purpose is to run image processing at a very large scale. We can also do things like moving object detection or human detection. So let me explain the architecture of our system. Our system is called CAM2, Continuous Analysis of Many Cameras. And it basically has the following components. First, it has a web portal. You saw earlier, it's the interface with users. And then it has a user database. We need to know who the users are, what they have done, and so on, including the programs they write. Then we have a camera database. Then there are, as I mentioned, quite a few cameras. We have about 70,000 cameras right now in our system. And the data goes directly from the camera to cloud. It doesn't go to our system because our system will be bottlenecked that way. A lot of study here is about resource manager because when I started the project, the purpose is to build a realistic environment to study resource manager in the cloud. That was the original purpose. But I wanted to build a real system so that the workload is real. And that's why we started the project in the first place. So later on, you'll see quite a few slides talking about resource management. This shows the distribution of a camera. Majority are in the United States. Simply, it's easier to do a web search. And we also go through Department of Transportation systematically. We have Purdue University has signed an agreement with about 20 states to get the data with their approval. The data is public, but we don't want to just grab the data because some of the states prefer us not to grab the data from their website. They want to grab the data from their other servers so that we don't slow down the website too much. Then the rest majority is in West Europe, again, because it's easier to do a web search. Some of the students are working on Asia and so on. So that shows the distribution of the cameras. Let me give a demonstration of one possibility of using this camera to do something we call real-time image-based navigation. This was done by a Google student and received an award last year. This is a very short video because each group, in a competition, each group has only 7 minutes to present. So he spoke really fast.
Here we're looking at our mobile application. And as you can see, it zooms and operates much the same way as our website application. We'll take a look at a few cameras in North America here before jumping over to Europe. This is a brief glimpse at a camera in Lawson. Over in Europe, you can see the clustering functionality works much the same way as the website application. And we'll take a look at a camera in the Mediterranean here before we get to the really interesting part of the mobile application. Here at the top, you can see me typing in 2 addresses, both in New York, a few blocks apart. And what the application is going to do is not only calculate the route between these 2 addresses, but it is also going to show me any cameras in our system between the 2 addresses. And so what this means is I can access the video feed from these cameras and take a live look at locations along my route, or I can look at my destination. So this might be interesting to me if I'd like to see if there's traffic perhaps, or what the day looks like outside if there are people walking around. In this look you can see that there's not much traffic. It's a sunny day, and so we would expect the same for the other cameras. I could also see, for instance, if there was a crowd outside of a restaurant I might want to visit, or any other sort of interesting data. The important thing is that I can take a live look at a destination or place important to me with this application. Here we're looking.
You may also notice that the frame rate there is about 1 frame a second. Any questions so far? Yes, please.
Is Cam2 grabbing the images from the cameras directly, or they're sending stuff into their own web server somewhere and you're grabbing them from the web server?
Okay, depends on the state, depends on the source. Some of them we grab the data from the camera directly. Some of them will grab them from their server. So Cam2 hide this behind the camera database. And as a user, you don't need to know. But if you want to help us add more cameras, you do need to know. Does that answer your question? Okay.
So
Yes.
I have to add new cameras then. For me to be able to be compatible with the Cam2 system, do I need any additional software?
Okay, so the question is, if you want to add your camera to our system, do you need additional software? The answer is no, because we have a layer to handle the heterogeneity of cameras. If your camera is, unless your camera is something very strange, and I don't expect that, our system already handles many different kinds of cameras. Some have high frame rate, some have low frame rate, some different brands have require slightly different ways to grab data. For example, some different brands, for example, Access. When you grab data, your query has a special, it's a brand specific path, and we encode that. Does that answer your question? So if you are to, unless you have a brand new camera, we don't know, if it's a commodity camera, we can handle it. And we can also grab data from a web server or FTP server, as you asked. For example, Texas told us not to grab from their web server. They want us to grab from an FTP server because I guess their FTP server has more bandwidth.
So when the user requests a camera, what is allowed? So you basically reroute the data to the user, or you actually store
Okay,
it?
so for the mobile demo, the data goes to the mobile device directly. Doesn't go through us.
So you basically are edges looking kind of.
Yes. So the mobile app communicate with the camera directly, and if you want to do analysis, and as I mentioned earlier, in this analysis, we go to the Amazon instances. That goes to the cloud directly. Doesn't go through our server, because we are very afraid our server becomes a performance bottleneck. In fact, we are pretty sure our server will not be able to handle this kind of load, because we don't have 17 machines, and these are the highest performance machines.
You're not storing anything, you told us, right?
We are not storing unless you ask us to.
Unless what?
You ask us to store
So
it.
what's the 7 terabyte data? That's
In
just coming
this
as
case,
just-
we don't store it. We grab the data, we process it, we throw it away. In this particular case, but you can store it. So let me go through a few more slides that may answer some of the questions. Okay, so as I mentioned, the system was built originally to study the resource management for cloud. So I put a lot of emphasis on cloud resource management. And what's the resource management problem? You select a group of cameras. let's say you want to study cameras in New York, and New York, those cameras have specific resolutions. Then you also give us analysis program. You may say, I want to count number of people. I want to detect a particular car. You can give us a program, and you tell us what the frame rate you want. Some of the cameras have a very high frame rate. Some cameras have a low frame rate. Of course, for low frame rate, we cannot give you more than what the camera give us. But some cameras have very high frame rate. You can say, I don't want a high frame rate. Even though the camera can give me 30 frames per second, I only want 1 frame per minute. You can give that number. Then we need to determine the cloud instances. What types, how many cores, how much memory. Currently, we don't use any special hardware such as GPU, but we are working on that. Then where the cloud instance should be, and how many of them. These are the locations of Microsoft Azure locations, and they are not equal. They are not equal in many different ways. One of the reasons is the price. For Microsoft, actually, I updated it only yesterday. In United States, the lowest cost, this is the D14. It has 16 cores plus 112 gigabyte memory. Per hour, you spend between $1.5 to $1.9. So difference is about 25%. For Amazon, the difference is much higher. For Amazon, the difference is up to almost 50%. So if you have a lot of data to analyze, that 50% make difference. So you may say, well, okay, it looks like it's cheaper to do data analysis in the United States. Should we move all the data to the United States? The answer is no. Because this I mentioned, why location matters depends on your desired frame rate. If your round trip time between a camera and the cloud instances are long, then your frame rate will drop. In this case, we use motion JPEG. This is measured, and we are we really appreciate that Microsoft actually gave us this data was measured using Azure. What we do is we select Google cameras, know their location. We launch the instances in different parts of the world. We measure a round trip time, and then we measure the frame rate we can achieve. Then this figure also shows two types of data. The more dots with the kind of yellow fill is measured. Then the black square are emulated by injecting delays using an emulator. So what we observe here is when the round trip time increases, the achievable frame rate drops for motion JPEG. What's the difference? What's motion JPEG? It encodes the video by a sequence of independent JPEG frames. Why do they do that? Because it's easier. It doesn't need to do motion detection between frames. It's also more robust. If one frame gets corrupted or one packet corrupted, the damage is only 1 frame. But the disadvantage is you need more bits for the data streams. Newer cameras support motion JPEG and also H.264. H.264, we observe the frame rate doesn't drop once the round trip time gets increased. However, there are more repeated frames. Still, if your round trip time gets too long, then H.264 still cannot keep up. So what it does is you will repeat frames. On the surface, the frame rate doesn't drop, but in reality, they still drop. So I think that answers your question about location. Right? Sorry it took so long to get here. You have to be careful about where you launch your cloud instances because that can affect the achievable frame rate.
So why is it that round trip time affects?
Because
is it not bandwidth?
Because motion JPEG is TCP based. Once you have round trip time long enough, your TCP outstanding window will it's waiting for the acknowledgement.
H.264 that shouldn't matter.
H.264, but we still see that. We actually haven't done enough studies to see why. But it doesn't wait for. It's not fully synchronous. Means it's not send a frame and wait for acknowledgement. But TCP, once it reaches the saturation.
Because you're just sending frame at a time, right? Explicitly. But H.264 is just a streaming. It's like
yes, but we still see that.
Netflix is sending you data.
Still, they basically will adjust, but we observe we haven't done enough measurement yet, but we observe in several cases the number of repeated frames increase as the round trip time increase. Repeated frame. So it will tell you you get 30 frames per second, but you also tell you these 2 frames are exactly the same. So you actually still see the jitter of a motion.
But do you lose frames or do you just see duplicates?
Okay, the question is, do we see loose frames or duplicates? I think we see duplicates. We don't know the frames are lost because we are only on the receiving end. We have no control of the cameras.
Is there any place you're getting 30 frames per second?
We have a lot, but this is a specific intention is to see whether we should. The question here is, should we move all the data to the United States?
But
Because-
there's this trade-off between compute and communications, right?
Yeah.
If you put a lot more compute, I mean, in the end, you're processing the data, and that's taking time as well.
True.
So you process it faster, you can take some delay, and then you can still you'll end up in the same
Okay,
place.
no. So the question is, can we do a trade-off between processing and delay? The answer is no, because we simply do not get the data.
That's different, though. You might get data, but if you don't process it in time.
No, this
it's
is
equivalent to-
measured. This is measured without processing. This figure.
Right, but what I'm saying is this is not accurate in that sense, right? Because
So
if
this
you're
is
not
the upper
processing
bound.
fast enough, your consumption rate is slowing down because you're not processing enough. That's equivalent
Right.
to not getting the data eventually
Well,
at the right time.
Yes, but this example is we grab the data, we throw it away. We don't do anything. So this data is the upper bound. This figure is the highest you can achieve. If you don't do any, of course, if you do processing, you'll further slow down. All right. Does that answer your question? Does that make sense? Okay. So this can be formulated as an optimization problem that you have different cameras. In this case, you have, let's say you have 3 cameras. And, excuse me?
Yeah, I have a follow-up. So you said that depending on what analysis somebody wants to do, well, this is the question. Do you actually understand that this analysis is going to need so much, this kind of an instance, to be able to start up a VM based on that upfront? Or is it something that the person or the consumer or the customer who's doing the analysis has to provide you?
Okay, so the question is, do we know if you run the program and we need to determine how many virtual machines to launch? Who knows that, right? It's somewhere in between. We don't know in advance, but we can launch your program and get a few data points, and then we extrapolate. In fact, that's my paper tomorrow. We'll be presenting in CalCon tomorrow. Is you give us a program, so let me go back to this slide. So you give us a program, right? Then we run your program on, let's say you want to analyze the data from 100 cameras. We'll launch your program, run your program on 10 cameras. We'll see whether we can meet the frame rate you want. If we can meet the frame rate you want, and then we measure the utilization. Let's say utilization is 80%. Then we'll say, looks like 1 cloud instance is good enough for 10 streams. We'll launch 10 instances. Does that make sense? Then then of course that measurement can change because your program behavior may change, the content may change. Then we'll observe and adapt. So maybe later on we find you need 12, then we'll launch more and redistribute the streams. And sometime later, maybe you need only 8, we'll consolidate. That's exactly my speech for tomorrow in Vancouver. Okay, I'm going to skip this slide. Then what's the frame rate you need? Depends on the study you want to do. If you want to study motion, you probably need high frame rate. If you want to study like the weather, you probably don't need a very high frame rate. So let me walk you through a few slides of the screenshot of our system to give you an idea how our system can be useful. This is an example of Los Angeles because a few years ago I gave a speech in UCLA, so I took Los Angeles as an example. As I said, we don't continuously save the data. We grab the data when you ask us to grab the data. So you can go to our system after you log in. You can go to our system. Let's say you select by locations. You go to Los Angeles, and then you select some cameras. As you can see, there are several hundred cameras here. After you select some cameras, you can also select camera by recent snapshot. We grab the 1 frame from each camera every 24 hours. We just have a program that will rotate randomly through the camera, and it takes about 20. We make our system very slow. We don't want to jam the network. So we grab approximately 1 frame. Actually, I believe it's 1 week, not 1 day. So we grab 1 frame per camera every so many minutes. You can also select by snapshot. And then you can specify, you can see here how many cameras you have selected, how long you want to run your program. You may want to run your program for only a few seconds, or maybe a few hours, or a few days, or maybe longer. You can say what's the interval between frames. If you are a user, we currently allow you to get 1 frame per second. That's the highest frame rate you can get. But if you are working with us, you can have a backdoor, you can get higher frame rate. Why do we do once per second? Because we haven't figured out what's the right answer. We simply set that limit. You can also specify how many frames you want to keep. Suppose you are doing some kind of motion detection. You may want to say, let's say, well, I want 10 frames. Then we'll give you a running window. If we get more than 10 frames, we'll drop the oldest, the 11th frame. We'll just give the latest 10 frames. So you can specify that number. And then you can upload your program. So I guess, sorry it takes so long to up here. You can upload a program, you write, or you can use a program we give you. We have written more than a dozen examples. These programs are written in Python right now. We are planning to extend to other languages, but we have not. We need more students, as always. But you can use our existing program as samples and modify them. Basically, if you imagine your program will most likely be something like a loop. You grab 1 frame, do some analysis, and grab another frame, do another analysis. The only thing you need to change is to change that while loop or for loop into our event-driven function. We have a paper published this year in Global SIP in electronic imaging that actually gives you the example. But once you log in as a user, you'll see all the examples we give you. Then we will decide which cloud instance to launch. And that's a problem we haven't solved yet. We have some progress, but we still have a lot of problems to solve. So which kind of instance we need to launch? How many cores? Some programs are more computation intense. Some programs need more memory. In fact, this example shows you that this is a very complex relationship, and it's not a linear relationship. Let me explain what this figure shows. So we show the utilization of a processor and the memory. And at 2 different frame rates. On the left side, we have 1 frame every 5 seconds. On the right side, we have 10 frames per second. You can imagine you have a very high frame rate. On the right side, it's processor intense. On the left side, it's not very low frame rate. It's some programs are processor intense. For example, human detection. And some other programs, such as motion estimation, it's bounded by memory. So the question here is, once you have the 4 different programs here, the image archival simply grab image and save it. Does not do any processing. Motion estimation, take 2 adjacent frames and estimate how much change has happened. Moving object detection, do a motion estimation, and then do a bounding box. So it's a little bit more complex. Then human detection is the most complex because you use the histogram of orientation to do the human detection. From this left side and right side, you can see human detection. We see in this particular instance using M3 X large, we cannot do human detection at 10 frames per second. So that's your question. If your program is too complex, computation is the bottleneck. On left side, if your frame rate is low enough, we can do more human detection. And this is per frame utilization. So if you want to say, for example, you want to do human detection, using this particular instance, you can do approximately 30 strings, right? Because you take maybe 40 strings. So the utilization, processor utilization, about 2.6% per string. and then you can process about 30-something strings, then your utilization become 100%. Does that answer your question?
Yeah.
Earlier? Okay. And I'm going to skip this. This simply says there is no simple answer. It's a very complex problem, and we are trying to build an empirical model, so we don't have to do this for every type of instance. This slide also shows that if you make a wrong decision, choose a wrong instance, you may pay more than twice. This data shows the price per million images. So if the bars are very much uniform, that means you pay the same price for different type instances. But on the right side, if you have 10 frames per second, the tallest bar is almost twice higher than the shortest bar. That means you pay almost twice the cost. We want to do that optimization, so we choose the right instance. Depends on your program is computation intense or memory intense, and some other factors. Earlier I mentioned our project is called continuous analysis of many cameras. This example is showing we count people over 24 hours. And these are the, over 24 hours, we actually see the number of people going up and down at different time. Actually sees very clearly that at night nobody's waiting for bus at the bus stop or even pass through. We do this for 1 frame every 10 seconds, and then we do a running average every minute. That's how we get a number. So if you want to do this kind of analysis over 24 hours, you can do that very easily by going to our system. As you can see, in the middle, it says the duration. If you specify a whole day, you can do that.
So who's paying for the computation?
Who's paying for computation? Right now, Microsoft and Amazon, because we get the research credit. Sometime in the future, maybe somebody else needs to pay. Also, our system is modular enough so we can switch the backend to your machine. Actually, when we ran out the research credit, we got renewed. But when we ran out, we just simply switch the backend to our lab. We cannot do very large scale processing, but we can do that. There are also related problem is what happens to the data you do not save. That's a very big question, and I don't have a very good answer yet. In cloud computing big data a few weeks ago, I presented some very initial ideas about the problem, but I think there are still a lot of problems to solve, so I won't take time here. So far, what I've talked about is the real-time data. You get the data when you process the data. A lot of cases, you have the data in advance. Maybe you save it, or you want to process it again and again. So save the data, and you want to process offline, not real-time data. And we also studied how to do this using SPA instance. You can think about SPA. You can think about using computer in several different ways. On demand, you pay by hour. It's like a hotel room. You can sign a long-term contract. It's like renting an apartment. Or you can do SPA instance by bidding the price. It's like Priceline.com. You give a price, you may get a hotel room, you may not. However, the SPA instance is different from Priceline because after you check into the hotel room, they may still kick you out if the market price goes above your bidding price. And when that happens, whatever you do is lost. Your intermediate result is lost. So what we do is we create checkpoint. We create periodic checkpoint so that when we get kicked out from the SPA instance, we can resume. Later on, we can resume from the checkpoints. And we find you can vary your bidding strategies. If your bidding price is about half of the on-demand price, meaning that if the hotel room, use an analogy, if the hotel room costs $200, your bidding price is $100, you have a very good chance to get it. We find we have about only 5% performance degradation, means we don't get it or we get kicked out. But that delay is about 5% only. But we can save 85% of the cost. The reason is the bidding price is the highest price you are willing to pay. What cloud may charge you is no more than your bidding price. So you may say, I bid $100, but you may get it at 70. That's the reason you can save up to 85% of the cost, but you have only 5% performance degradation. So that can save a lot, particularly if you have a huge amount of data. That saving is significant. I think I've told you quite a few interesting problems. I would say what we have done is only a very small portion of what can be done. I call it the tip of the iceberg. The more study we have done, the more papers we write, the more problems we discover, and the more people we talk to, and the more people we want to talk to. Now I have talked to people doing, as I mentioned earlier, doing psychology, doing forest research, doing transportation research. But there are still many, many problems. One problem is the metadata. Currently, there is no easy way to get metadata. We don't know where the cameras are. We don't know their frame rate. There's no easy way to get. We don't know what's looking at. Is it indoor or outdoor? Can you see people? Still, there are a lot of things we need to work on. We are working on some automatic method to generate metadata. Another problem is there's simply no standard of getting data. Different brands of cameras have different methods. And different states have their different way of giving you the data. It all shows up on website for humans to see, but it's not designed for machines to grab the data. But I've already mentioned camera. At the end, what we want to do is to use the system to understand the world. So obviously, there are a lot of opportunity for vision research. One colleague was doing the machine learning, so he asked me to give him some data as his sample, asking how much do you want. He said, how much can you give me? So I gave him 100,000 images from New York City at 1 frame per second from 12 traffic camera over 4 hours. So he said, well, that's good enough for a while. He was trying to see how he can detect the same car from moving across several different intersections. I have talked about resource allocation. That's, as I mentioned, that's the original purpose of building a system. And privacy always come up. When I was in Australia, I find this very nice location. So I took a picture of it. It tells you are being recorded. Our project uses only publicly available data, and we are cleared by Purdue legal department that we don't have any privacy concern. But privacy is always a question. I have done some studies about the legal status about cameras. My understanding is there still need to be worked out. I think this morning when I was at the airport waiting for the flight, I saw several cities decided to give each police person a camera because there's some recent instance. So what's the privacy issue there? If a police has a camera, body camera, who owns the data? I think that still needs to be worked out, and I'm not an expert on that. You
don't see these issues because you started by saying you're just tapping into public feeds, right?
Yes.
So basically you bypass all those issues.
We only use public data.
You're not the ones deploying cameras.
We are not the one deploying cameras.
Deploying it, somebody else is grabbing it, and they're publicly available, so there's not much issue here.
Correct. But when we are looking for cameras, we also find some cameras, they are publicly available, but we don't want to use our system. For example, we find some cameras, we believe they are looking like somebody's living room or something. Why are they public? I don't know. But we find them, but we don't want them because we don't want to deal with that. This is a big project, and it's also a very good experience for a lot of students, many of the undergraduate students. This is, I think for probably all of them, this is the biggest project they've been working on. It's a very big team for them to have that experience. And I'm also very fortunate to have a funding support from National Science Foundation. And of course, Microsoft gave us the research credit to use Azure. That's very, very helpful for us to do some study. To conclude, I hope I have given you the idea that network cameras can be very useful for a lot of studies. On Wednesday in CloudCon in Vancouver, there will be a panel discussion about network cameras and cloud computing. I'm one of the panelists. I think there are still many, many challenges. From the many questions here, I can see there are a lot of questions, and we have answered only a very small fraction of a lot of questions. But I hope I have given you the idea that we are building something useful. It's an open system for people to use. You can register as a user. And if you want to get the source code, we can also work out some agreement. We have already signed agreement with a few universities about sharing the source code. Our legal department will be able to work out these details. As I mentioned, our system is not an archival data. It's a computing platform for you to run programs, and we do everything for you, including, in particular, allocating cloud resources. With this, I want to thank you for your attention.
So these programs that people write to analyze, do they have to be in a certain format? I mean, how do you have some APIs?
We have an API. Basically, your program need to include a few import, a few modules, and you have to create a derived class of a specific class we create, and then it's an object, so we handle majority of work in the base class. But you have to override a few methods for your purpose.
But the quantum is just one frame, like
currently we do one frame. Yes, but you can get the past frames. So you can say I want the past 10 frames, and then you can get, let's say, the last 3 frames. You decide what you want to do. And we run the running windows. Let's say you want to keep 10 frames, we just keep the 10 latest frame, and the old one get dropped out. But you can specify the number 10 or 12 or whatever.
So where do you see all this evolving besides making it all robust and all?
So
what is the next big things that you are?
What do we want to do with this? First, we want to use this system to do some studies, interesting studies. I mentioned psychology, civil infrastructure, transportation, and forest, and so on. And use this system for people to do machine learning, because we have huge amount of data for them to use. Let me talk about machine learning a bit more, because it seems to be a hot topic these days. For example, we know the precise location of some cameras. For example, New York City, they each give us the coordinates at each intersection. And we can map that into, for example, a bus route. So you know a bus will come from one particular intersection to another particular intersection. And then you can use that meta information to train your bus detection program. And remember this, bus may not be in the same lane, and even in the same lane, the camera angle may be different. So it becomes a very rich resource of doing all kinds of studies. So we want to provide that infrastructure. And I mentioned the psychology study. We want to use this data for people to do observation, non-intrusive observation of people worldwide. Does that answer your question? I'm also the organizer of a low-power image recognition competition. So this can also be used as the source of data. I have not combined these 2 projects yet. So far, the 2 projects are still separate. But this can be a source of data to use. As many of you may know, good data is often the foundation of many interesting research, and we are building a system to provide good data. Does that make sense?
Sure.
Okay.
Sure makes sense. Okay.
Other questions?
Other questions? All right, thanks, Brian.
Well, thank you very much. I'll be here.